AGI is a topic on the lips of anyone in artificial intelligence. Recently, one ex-OpenAI employee has written a paper titled Situational Awareness, in which he is addressing the current and future situation of AI. In this video, I will only be giving my thoughts on his first chapter, which he titled From GPT-4 to AGI, Counting the OMs. He states that AGI is very plausible by 2027, arguing that GPT-2 to GPT-4 took us from preschooler to smart high schooler abilities for years. Tracing trend lines in compute, 0.5 orders of magnitude or OMs per year, algorithmic efficiencies, 0.5 OMs per year, and unhobbling gains from chatbot to agent, we should expect another preschooler to high schooler-sized qualitative jump by 2027. He starts by talking about the rapid progress of AI we have seen in the last decade. He claims that we should not have been amazed by the capabilities of GPT-4 given the pace of change in the last decade. But GPT-4 was merely the continuation of a decade of breakneck progress in deep learning. A decade earlier, models could barely identify simple images of cats and dogs. For years earlier, GPT-2 could barely string together semi-plausible sentences. Now we are rapidly saturating all the benchmarks we can come up with. And yet this dramatic progress has merely been the result of consistent trends in scaling up deep learning. He continues by saying, I make the following claim: it is strikingly plausible that, by 2027, models will be able to do the work of an AI researcher or engineer. That doesn't require believing in sci-fi. It just requires believing in straight lines on a graph. In the graph, he shows the rate of growth of effective compute year on year. Rough estimates of past and future scale-up of effective compute, both physical compute and algorithmic efficiencies, based on the public estimates discussed in this piece. As we scale models, they consistently get smarter, and by counting the OMs, we get a rough sense of what model intelligence we should expect in the near future. This graph shows only the scale-up in base models. Unhobblings are not pictured. Publicly, things have been quiet for a year since the GPT-4 release, as the next generation of models has been in the oven, leading some to proclaim stagnation and that deep learning is hitting a wall. But by counting the OMs, we get a peek at what we should actually expect. He then continues to paint the picture of the growth in the order of magnitudes from GPT-2 to GPT-4. How we have moved from preschooler in GPT-2 to an elementary schooler in GPT-3 to a smart high schooler in GPT-4. The pace of deep learning progress in the last decade has simply been extraordinary. A mere decade ago, it was revolutionary for a deep learning system to identify simple images. Today, we keep trying to come up with novel, ever harder tests, and yet each new benchmark is quickly cracked. It used to take decades to crack widely used benchmarks. Now it feels like mere months. We're literally running out of benchmarks. As an anecdote, my friends Dan and Colin made a benchmark called MMLU a few years ago in 2020. They hope to finally make a benchmark that would stand the test of time, equivalent to all the hardest exams we give high school and college students. Just 3 years later, it's basically solved. Models like GPT-4 and Gemini get 90%. How did that happen, though? Counting the order of magnitudes shows how the pace of growth has been consistent. He says we can decompose the progress in the 4 years from GPT-2 to GPT-4 into 3 categories of scale-ups. The first is compute. We're using much bigger computers to train these models. The second one is algorithmic efficiencies. There's a continuous trend of algorithmic progress. Many of these act as compute multipliers, and we can put them on a unified scale of growing effective compute. And the third one is unhobbling gains. By default, models learn a lot of amazing raw capabilities, but they are hobbled in all sorts of dumb ways, limiting their practical value. With simple algorithmic improvements like reinforcement learning from human feedback, RLHF, chain of thought, COT, tools, and scaffolding, we can unlock significant latent capabilities. He continues to say that we can count the OMs of improvement along these axes. That is, trace the scale-up for each in units of effective compute. 3x is 0.5 OMs. 10x is 1 OM. 30x is 1.5 OMs. 100x is 2 OMs, and so on. We can also look at what we should expect on top of GPT-4 from 2023 to 2027. I'll go through each one by one, But the upshot is clear: we are rapidly racing through the OMs. There are potential headwinds in the data wall, which I'll address, but overall, it seems likely that we should expect another GPT-2 to GPT-4 size jump, on top of GPT-4, by 2027. He starts with compute, which is by far the most discussed driver of the acceleration we are seeing in deep learning, all thanks to NVIDIA. The compute scale-up from GPT-2 to GPT-3 in a year was an unusual overhang, but all the indications are that the longer run trend will continue. The SF rumor mill is abreast with dramatic tales of huge GPU orders. The investments involved will be extraordinary, but they are in motion. He continues with this discussion on compute in Chapter 3, which he titled Racing to the Trillion-Dollar Cluster. Based on that analysis, an additional 2 OMs of compute, a cluster in the $10 billions, seems very likely to happen by the end of 2027. Even a cluster closer to plus 3 OMs of compute, $100 billion plus, seems plausible and is rumored to be in the works at Microsoft/OpenAI. On algorithmic efficiency, he separates 2 kinds of algorithmic progress. He starts by covering within-paradigm algorithmic improvements, those that simply result in better base models and that straightforwardly act as compute efficiencies or compute multipliers. For example, a better algorithm might allow us to achieve the same performance but with 10x less training compute. In turn, that would act as a 10x or 1 OM increase in effective compute. If we step back and look at the long-term trends, we seem to find new algorithmic improvements at a fairly consistent rate. Individual discoveries seem random, and at every turn, there seem insurmountable obstacles. But the long-run trend line is predictable, a straight line on a graph. Trust the trend line. We have the best data for ImageNet, where algorithmic research has been mostly public, and we have data stretching back a decade, for which we have consistently improved compute efficiency by roughly 0.5 OMs per year across the 9-year period between 2012 and 2021. That's a huge deal. That means 4 years later, we can achieve the same level of performance for 100x less compute, and concomitantly, much higher performance for the same compute. The third and final metric he uses is that of unhobbling gains. It is very hard to quantify, but one that is of massive significance in determining the future path of progress. He starts by giving this thought. Imagine if, when asked to solve a hard math problem, you had to instantly answer with the very first thing that came to mind. It seems obvious that you would have a hard time, except for the simplest problems. But until recently, that's how we had LLMs solve math problems. Instead, most of us work through the problem step by step on a scratchpad, and are able to solve much more difficult problems that way. Chain of thought prompting unlocked that for LLMs. Despite excellent raw capabilities, they were much worse at math than they could be because they were hobbled in an obvious way, and it took a small algorithmic tweak to unlock much greater capabilities. We've made huge strides in unhobbling models over the past few years. These are algorithmic improvements beyond just training better base models, and often only use a fraction of pre-training compute, that unleash model capabilities. The few unhobbling techniques that have shown tremendous improvements include reinforcement learning from human feedback, RLHF. Base models have incredible latent capabilities, but they're raw and incredibly hard to work with. While the popular conception of RLHF is that it merely censors swear words, RLHF has been key to making models actually useful and commercially valuable. Rather than making models predict random internet text, get them to actually apply their capabilities to try to answer your question. This was the magic of ChatGPT. Well done. RLHF made models usable and useful to real people for the first time. Chain of thought. COT started being widely used just 2 years ago and can provide the equivalent of a greater than 10x effective compute increase on math and reasoning problems. Scaffolding. Think of COT++. Rather than just asking a model to solve a problem, have one model make a plan of attack, have another propose a bunch of possible solutions, have another critique it, and so on. For example, on human eval specifically, coding problems. Simple scaffolding enables GPT 3.5 to outperform unscaffolded GPT-4. Tools. Imagine if humans weren't allowed to use calculators or computers. We're only at the beginning here, but ChatGPT can now use a web browser, run some code, and so on. Context length. Models have gone from 2,000 token context 4, GPT-3, to 32,000 context 4, GPT-4 release, to 1 million context 4, Gemini 1.5 Pro. This is a huge deal. A much smaller base model with, say, 100,000 tokens of relevant context can outperform a model that is much larger but only has, say, 4,000 relevant tokens of context. More context is effectively a large compute efficiency gain. More generally, context is key to unlocking many applications of these models. For example, many coding applications require understanding large parts of a code base in order to usefully contribute new code. Or if you're using a model to help you write a document at work, it really needs the context from lots of related internal docs and conversations. Post-training improvements. The current GPT-4 has substantially improved compared to the original GPT-4 when released, according to John Schulman, due to post-training improvements that unlocked latent model capability. After discussing the gains that unhobbling would bring to models, he tries and quantify the orders of magnitude that we should expect in order to achieve AGI by 2027. First, he shows that from 2019 to 2024 the growth was in the rate of orders of magnitude of about 4.5 to about 6 OMs. He then looks at the journey ahead and predicts growth of orders of magnitude of about 5 OMs for compute and algorithmic efficiency only. With these, he argues that by adding unhobbling gains we can move from a chatbot to a coworker and potentially to an AI researcher. After reading this, I feel that 2027 is the most optimistic year we can come up with. It is guaranteed that by the year 2027, we shall have made huge gains in artificial intelligence. But shall we have AGI by then? That I cannot say. I feel that unless we can first have a unified definition of AGI, it would be too optimistic to talk of AGI. It may one day come, but if we are to know how to achieve it, we shall need to have a definition of what it is. Again, we need to have a clear debate between the proponents of AI as intelligence versus AI as curve-fitting mechanisms. I would like to hear your thoughts on this. Leave a comment below and consider subscribing for more.